the high quality satellite imagery that is required for many applications, there is a kind of illusion that it's available. There are lots of companies that provide it, but in reality, there's enormous gap between high quality, high resolution commercial satellite imagery that is extremely expensive and not economically viable for most applications. And then there is the low resolution imagery that is publicly available, which is amazing, but it's not good enough. It doesn't have resolution that is high enough and the quality that is necessary for most of these applications. You have rods that are mixed with the crop. You have widths that are mixed, like everything is mixed together. 10 by 10 meter pixel, it's a huge pixel, okay? And so this prevents any development of really reliable analytics, because what you are measuring is not really, everything kind of is a mess. Satellite imagery, wherever you need it, whenever you need it. Okay, that was always the holy grail of the Earth observation industry, right? And so far, never materialized. It never happened. You cannot ask, can I have 1 meter per pixel cloudless image of, point XY from 2 weeks ago? You cannot, like, not at any price, okay? You can try to task something, you would pay thousands of dollars because there is a minimum tasking size. So you will pay, I don't know, I don't remember, but $3,000 at a minimum to get a 1 meter per pixel image. And chances are, depending on geography, it will take you 2 months to get it because of the clouds. Okay. And then once you get it, it will be expectedly uncalibrated and completely useless for most cases other than defense, Any analytics has a margin of error, and any analytics hopefully has some practical utility. So the question is whether a particular statistical or analytical model is good enough for a given practical application. That's the question at hand. It's not ideological question. It's not about, for me at least, it's not about ideology. It's about practical utility. Is it good enough to solve the problem at hand? Right? Because a lot of people come with some deeply ideological kind of approach that it shouldn't be used because it's somehow fundamentally different from any linear, regression. Okay, linear regression is a very simple statistical method that has a margin of error. It can overfit, it can hallucinate, it can do all of these things, exactly the same as neural network. The question is whether they use the right training data, whether the training data matches your real world data, and whether the margin of error is sufficient for your application. That's all.
Hi everyone, in today's episode I'm with Yosef from Gamma Earth. Yosef, could you please explain the history of your company and what products do you provide?
Sure. Hi, Louis. I have a very tactical background. I spent many years in academia doing research in remote sensing and Earth observation, and also some mobile robotics, signal processing. And then I started a company called Gamma in the sector of agtech, using drones and satellites to provide analytics for farmers to try to improve decision-making process and automate some of the decision-making. And the company is still going, it's still moving forward, but I left a while ago and I decided to focus on one particular bottleneck that I discovered while being at Gamma, is that there is actually the high quality satellite imagery that is required for many applications. There is a kind of illusion that it's available. There are lots of companies that provide it, but in reality, there's enormous gap between high quality, high resolution commercial satellite imagery that is extremely expensive and not economically viable for most applications. And then there is the low resolution imagery that is publicly available, which is amazing, but it's not good enough. It doesn't have resolution that is high enough and the quality that is necessary for most of these applications. So between these two extremes, there's an enormous gap, and nobody manages to provide a solution there. So I decided to really focus on that. And the way that I decided to address this is to take satellite imagery, mid-resolution, which is 10 meter per pixel, available from European Space Agency, from Sentinel-2, and try to improve it using some of the state-of-the-art neural networks, artificial intelligence, as it's called, improve the resolution and reconstruct some of the spatial details required for some of these applications. And that's exactly what I'm doing now. I have a couple of models, one that is doing super resolution, so converting 10 meter per pixel imagery from Sentinel-2 to 1 meter per pixel. And then the second model that is really just now is getting ready for release is the cloud mitigation model that allows you to actually provide guaranteed cloud-free imagery, which is, I believe, which is really necessary for a lot of these commercial applications. So that's what the company does. Gamma Earth tries to provide reliable, high revisit rate, cloud-free, high quality, high resolution, and most importantly, low cost satellite imagery data.
And who are the clients for such data?
Right. So at the moment, it's mainly Agtech. So there is Agtech, so agricultural technology, the whole segment of companies that are developing analytical products from satellite and drone imagery for farmers, as we used to do in Gamaya, and Gamaya still does. And then there is a large and kind of emerging sector of carbon credits. So companies that manage carbon credits and need to analyze and kind of verify various processes that happen on agricultural fields, but also natural resources. These are the two main sectors that I feel there is a strong demand for what I'm doing right now. But there are also some other important sectors such as mining and in general resource management. That's I believe that will be a strong demand from these sectors.
Yes, for agriculture, most of the products use low resolution, so 10 meter sentinel data. Do you see specific reasons why the high resolution will be more interesting?
Yeah, certainly. So de facto, this sector is kind of people are experimenting with different things, but it doesn't stick. There is no real success stories in this sector, despite the fact that there are dozens and dozens of companies trying different things, but nobody managed to really scale this business and develop a reliable, profitable business model. There's just no such success stories to the best of my knowledge. Now, the reasons there are multiple reasons, and availability of satellite imagery is definitely a significant factor. And the problem is that 10 meter per pixel, while it depends on the context, and in very large fields such as you have in the United States, in some of the in Brazil, some of the really large scale industrial agriculture, it sounds like it would be sufficient, and in some marginal cases maybe it is. But in reality, you have a situation where everything is mixed pixels. You don't have clean separation between spectral characteristics of different types of vegetation. You have rods that are mixed with the crop. You have weeds that are mixed. Like everything is mixed together. 10 by 10 meter pixel, it's a huge pixel. Okay. And so this prevents any development of really reliable analytics, because what you are measuring is not really everything kind of is a mess. And then the second factor, very significant factor, is that farmers, 10 meter per pixel, 10 meter, it's not a human scale. And so it's very counterintuitive. When farmers see their fields at such a low resolution, they have really difficulty to relate to what they're seeing. They don't see their house, they don't see the road, they don't see the trees, they don't see any. Humans have a very intuitive approach to imagery, and they need to somehow relate to the objects that they're used to see, okay? And 10 meter per pixel satellite image doesn't give them this possibility. And so I feel farmers, there was a very slow, like this data is available for many, many years, and de facto farmers just don't buy in because it's not something that they can relate to. And I think going to 1 meter per pixel, while it's actually human scale kind of imagery where people can identify and relate to objects that they used to see, this is definitely will be very significant advantage for them to start trusting this data and starting relying on it.
So I guess it depends on the application, if it's for yield prediction or maybe for precision hydration. Maybe the different applications don't have the same resolution need also.
This is certainly true. It's absolutely true. However, the problem is, let's say that you have a kind of 10 different analytical products that you feel that the market needs, okay? But the data that you have access to allows to actually do only 2 out of 10, okay? And so you end up with something that, okay, maybe somebody will be kind enough to look at, but it's not really something that brings a lot of value and is particularly helpful to the farm. So sure, it's all depends on the use case. It depends on the application. Also, as I said, there are some very large fields when these large pixels would make more sense. But there are also very small fields. Most of the world have, farms where fields are 1 hectare, and so you don't see anything at all. You can't even separate there's not enough pixels to see individual fields. And so most certainly, I feel that this data allows you to make a significant progress over the status quo.
Let's get into the debates about super resolution, because I guess you're probably confronted with a lot of skepticism with the reliability and how close the data is to the actual truth. Could you talk a bit more about this controversy and why you believe that super resolution data is valuable?
Sure. So I'll first start a little bit with kind of introduction to say that people have this, and to a significant extent it's justified, this perception that this neural networks and AI is something that is fundamentally different from conventional statistics, okay? And this is justified to some extent, but I think people overthink it because any analytics is an estimation, okay? Any analytics has a margin of error, and any analytics hopefully has some practical utility. So the question is whether particular statistical or analytical model is good enough for a given practical application. That's the question at hand. It's not ideological question. It's not about, for me at least, it's not about ideology. It's about practical utility. Is it good enough to solve the problem at hand, right? And exactly the same way, AI neural network-based analytical models, they have margin of error. A particular model has a margin of error. It has particular utility, and then you need to validate it and see whether the produced result is good enough for you to solve the problem that you have to solve. Okay? And that's what I'm trying to do. I'm trying to validate these use cases. I'm trying to see whether the output of the model is good enough to address different practical applications. Now, I have conducted extensive study and I published the results, trying to demonstrate and validate how accurate the model is and what is the margin of error, right? So I extensively and really detailed that there are artifacts and there is margin of error, and this is how it, like, I really put a lot of work in trying to document it. And then the next question is, okay, if please, I have open access model that I published that people can use, validate, experiment with, try with the application. And the whole point is that, okay, there are people that definitely find it useful. I have dozens of, researchers that use it, commercial and academic that use it. So that it's definitely useful. Okay. The question is, what is it useful for, right? So I invite anybody to try it, experiment with it, test whether it's good enough for their use case. And if not, I'm not forcing anybody to use it. It's as any other statistical model, okay? It's an estimate. A lot of people find it amazing and useful, but probably not everyone. And that's, it's a free economy. I'm not forcing it on anybody. So that's kind of, for me, what solves the problem is that removing ideology out of it. Because a lot of people come with some deeply ideological kind of approach that it shouldn't be used because it's somehow fundamentally different from any linear, regression. Okay, linear regression is a very simple statistical method that has a margin of error. It can overfit, it can hallucinate, it can do all of these things, exactly the same as neural network. The question is whether they use the right training data, whether the training data matches your real world data, and whether the margin of error is sufficient for your application. That's all.
I guess the origin of the controversy is because people have an instinctive attitude towards the fact that you can't really create information. My understanding is that there is a very high correlation between the low dimensional or the low resolution pixels and the higher resolution pixels. And also there is a high correlation between pixels spatially. So maybe a legitimate criticism could be if there is something which is very surprising. So let's say some blue trees suddenly appear, then the model will have high difficulty with being accurate on this edge case or this statistically surprising phenomenon.
That is absolutely 100% correct. Yes, yeah. The model is struggles with things that it never seen before. This is absolutely right. But most of the things look like most of other things. There are some few things that look differently. But especially in agriculture, especially in the resource management and forestry and all of these applications, for the most part, things look like most other things, okay? Things are very regular, repetitive, and rather predictable. Now, not always. So, for example, there's this very interesting artifact that kind of actually found its applications, but it wasn't, it was unintended. That if you have an open fire, right, it kind of creates this. So open fire is, the resolution is not enough to see the fire, okay? So there is no fire visible in RGB channels. However, it generates a very high level of radiation in shortwave bands of Sentinel-2, okay? And so when you super resolve, it creates kind of this visible blobs of orange, which are kind of exaggerated fire. So that is because there's no open fire in the training data sets, and it struggles to reconstruct this correctly. But it appears that actually it has its useful applications because it's kind of, you can detect open fires very easily. But it's your analysis is completely correct. When it sees something that has never seen before, it will likely generate artifacts.
I'm wondering also what are the limits of the technology. Instinctively, it will be improbable to have to push the technology to have it read a newspaper, let's say, of someone in the park. To what extent can you go in super resolution? And are there some instances where it's easier than, is it, for example, easier in fields than in urban environments, or is it not necessarily the case?
So all of those, there's definitely limits and the variations, both in terms of types of terrain and availability of training data. So some regions in the world are better represented in training data than others. And the best things that are reconstructed are agricultural. Actually, agricultural surfaces are the best reconstructed because they are very large scale and they are very periodic. Okay. And so they're kind of repetitive. And so they're very, sometimes really surprisingly well reconstructed. Urban environments depends. There are some regular urban environments that are reconstructed really well, but there are also irregular urban kind of small scale somewhere in India that are almost impossible to reconstruct. So then there is a lot of variability, and I think again the key is to focus on particular use cases and applications and to figure out whether it's good enough for what you're trying to solve, because this is a purely utilitarian method, right? This is a utilitarian technology. This technology was not developed to prove any point. This technology or break any laws of physics or mathematics. This technology was developed to solve certain practical challenges. And so if it manages to do that, that's exactly what I'm aiming at.
I guess there will be also some financial challenge, because I imagine if you're developing a large scale application with a model, using high resolution data will be more expensive because you have more data to feed the model. The model will then also have, it will be easier for the model to recognize some features, some details. I guess someone who's trying to develop an application will probably think of the trade-off. Should I train my application on the low resolution data? And therefore I need to, in my model, integrate the super resolution part, or should I use super resolution data and have more data, but then probably the training part of the model will be easier, and they will have there will be higher accuracy on the training part.
Yeah, there is a very interesting point here that if you in all of these applications, the bottleneck is always training data, right? So the model itself became relatively standard. There are a few standard architectures that everybody's using, and it's copy paste. The problem is, can you actually build relevant, accurate training data sets? And the thing is that for most of these classification applications, actually, unless you see and you can manually classify, right? You can seed some people to manually classify, but you can't build training data sets. It depends on the applications. But if you are looking at some classification use case, then somebody needs first to see what you are trying to classify, recognize it as the particular type of objects that you want to recognize, and then to manually classify, to build a training data set. And the problem is that without super resolution, you can't actually see, right? So you can't build training data sets. So for example, a notable example is the field delineation, which is a very big part of what we do. The problem is that you cannot manually draw field boundaries, okay, on original Sentinel-2 imagery. It's that the boundaries are not defined well enough to draw them, right? So the only way that we could find how to do this is to super resolve then on super resolved data manually draw the boundaries, okay, and then build training data sets, and then train the model that would convert super resolved data into field boundaries. Does it answer your question?
Yeah, it does, yeah.
So building training data sets is most of the time the bottleneck. And unless you have super resolved data that is kind of human scale that somebody can recognize and classify, you actually can't build training data sets.
And so for you, what is the long-term use of high-resolution satellites commercial data? Is it only for building training data sets?
For me, these two products, the super resolution and the cloud mitigation, right? This is what I may be wrong, but this is what the industry always wanted to achieve. You always want to get to the point where you have human scale satellite imagery. And I mean by human scale, I mean meaningful, useful satellite imagery wherever you need it, whenever you need it. Okay, that was always the holy grail of the Earth observation industry, right? And so far never materialized, it never happened. You cannot ask, can I have 1 meter per pixel cloudless image of point XY from 2 weeks ago? You cannot, like, not at any price. Okay, you can try to task something. You would pay thousands of dollars because there is a minimum tasking size. So you will pay, I don't know, I don't remember, but $3,000 at a minimum to get a 1 meter per pixel image. And chances are, depending on geography, it will take you 2 months to get it because of the clouds. Okay. And then once you get it, it will be expectedly uncalibrated and completely useless for most cases other than defense. If you want to see a particular truck or whatever, something military there that human analysts can look at, maybe that's what it's used for. But everything else, it's completely not economically viable and also impractical, right? So first you can't get it, and if you can get it, it's 2 orders of magnitude more expensive than any commercial application can support. And so I'm trying to solve this. Now, whether what I'm doing right now is enough or not, it's a question, but I feel definitely I'm on the right track. I can today produce cloud-free 1 meter per pixel spectrally calibrated image at very low cost on any date at any location on the surface of the Earth. And I think that's what the entire industry always wanted to get to.
So for the cloud removal, you use SAR data. What are the similarities between the super resolution models and cloud removal models?
Well, cloud removal is much more complex. Super resolution is using a single scene of Sentinel-2. Cloud removal uses multiple scenes of Sentinel-2 and is trying to basically make an estimate, okay, of what is the most likely the appearance of the surface on this date, on this location. That's all there is to it. There's no SAR because I experimented extensively with SAR with Sentinel-1, but I didn't find it useful. So it's only Sentinel-2, it's multiple scenes, and it's an best estimate of what the surface should look like based on the history, but based on the spatial context, based on a lot of different things. And again, same as super resolution, it's an estimate, it's a stochastic model. Whether it's good for your particular application is a question of this particular use case. There will be some that probably it won't be good for, but I'm absolutely certain that there are lots of applications whether this can be a fantastic source of very reliable data. And the simplest way, I think, to put it is by far the best option. There's no alternative. It's not perfect, but there is nothing even remotely close in terms of quality and availability.
You also worked on radiometric calibration.
Yes.
Can you maybe explain what this is and what are the challenges?
I mean, this is a very complex, it's a whole science in itself. The thing is that a lot of people talk about, multispectral. Now, I have a background actually in developing instruments for hyperspectral imaging, for spectroscopy, imaging spectroscopy, what it's called, okay? And what I think some people overlook is that it's not enough to have lots of spectral readings. You need to calibrate them. They need to mean something. It's like a thermometer, okay? There's the scale on the thermometer, but you need to know what the scale means. If you don't know whether it's Celsius or Fahrenheit, what it means, the scale, it's not of much use, right? And so if you just create, let's say, hyperspectral camera or multispectral camera, right? And then you put up a satellite in orbit, and then the satellite takes some images, and you have lots of data, right? But this data it went through the atmosphere. It got reflected. So the light came from the sun. It went through the atmosphere. It got reflected from the surface, and then it hit the sensor. You need to somehow relate what you want to measure are the property of the surface, right? So what it's called, you want to measure the spectral reflectance. You want to understand how your readings, right, the digital numbers that you recorded, relate to the physical properties of the surface that you are imaging, right? However, what you are measuring is not that. It's something that went, again, twice through the atmosphere. And if the sun, let's say 2 hours passed and the sun moved, you will get a completely different reading, okay? But the physical property of the surface that you are imaging has not changed, right? So you need to find a way to separate between these two effects, because if each minute that you are imaging, if you get a different reading and you don't know to take this into account, this data is useless. It doesn't matter how many bands you have. You can have 1,000 bands and it's of no use. Okay. And there are some very complex models of how do you do that, how you calculate reflectance. And the best model that is available right now is actually from Sentinel, from European Space Agency. Is by far the best calibrated imaging satellite that is available today. It's much better than, for instance, than NASA's Landsat. However, again, it's not perfect. It's the best there is, but it's not perfect. There are lots of effects that it doesn't take into account. For example, the most notable, it doesn't account for the orientation of the surface. So if the surface is, let's say that you have exactly the same kind of surface, okay, with exactly the same spectral characteristics, but it's oriented differently in relation to the sun and in relation to your camera, you'll get a different reading. And Sentinel-2 would not know how to deal with this. There are new models, there are new research, and I keep in touch with people who work on solving these problems. There's a calibration, atmospheric correction model that takes into account the orientation of the surface. So it's very active scientific and technological field of development. Yeah, but again, so it's another step forward, but even this is still not perfect. So I'm not sure I wouldn't go into much really technical details. There are books that are written about this, but it just to emphasize the complexity and the importance of this issue. And I have to say that, unfortunately, this is very underappreciated, the subject. And there are lots of, there are many startups right now it's very kind of very high point for hyperspectral satellites. And the startups, in my experience, know very little about calibration, and they just don't appreciate how complex and important this challenge is. So they will have it coming for them once they will start to try to use this data for any practical application.
Although I guess the good news is that it's a software problem, so you can always take the data and try and create a model afterwards. Or I mean, do you need to take into account this problem, during the sensor design?
There is no simple answer to this. You are right to some extent. So ideally, you take it into account because there are lots of things that you can do. You need to do, but this is kind of a little bit better understood. You need to have extremely well calibrated sensors on board. So you need to know exactly how your sensors behave, and there is a lot to do in terms of calibration before the sensor is deployed. You're absolutely right that a lot of it is done in post-processing, and even, for example, European Space Agency for its Sentinel-2, there are constantly updates for the processing pipeline and the atmospheric correction pipeline. There are even each image has multiple versions where they first calibrate it, they process it, they release it, publish it, and then they reprocess it because there's some update to the processing pipeline. And so they publish updated image. So there is this enormous amount of data engineering and complexity involved. And I was involved in this as part of my work at Gamaya. We've been developing hyperspectral sensors for drones, and we spend a lot of time trying to calibrate them. And so I have some technical insights. I also was involved in design of hyperspectral satellites. So I have some knowledge, but it's not, as you will see, this is not my main area of expertise. It's just something that I am aware of importance of and have quite a bit of insights on.
Maybe we could talk a bit more about the future applications that you see for in Earth observation. I mean, many startups have the impression that they can just produce data and use cases will magically appear. What's your take on this? And do you see any areas where the data will be very relevant?
My opinion that they're mistaken, that there's very little in general. There's kind of a set of things that can be technologically done, and then there are a set of things that are actually required by the market, so have practical utility, okay? And there's already very little overlap between these two sets. But there is a third set of things that are economically viable, right? So you can have things that are technologically possible and same things that have practical utility and people are ready to pay money for, and still you will not have a business because it's not economically viable. It takes too much effort and money to deliver this service than what people are ready to pay for, right? So the overlap between these three sets, what is technologically feasible, what is practically usable, and what is economically viable, is extremely small. Okay, and so, but it's a case by case basis. You need to very carefully review and find these niches, and in most startups don't do it. As a result, startups rarely succeed. But it's definitely something that I would very strongly recommend from the get-go. You don't need to cover all of it, and you don't need to find lots of them, but you absolutely have to make sure that there are some, I don't know, a few practical applications that you are certain that somebody is ready to pay for before you start putting a lot of effort and resources into developing the technology. I mean, it's for that you have lots of universities that do it differently, or big corporations that invest in research, blue sky research, and it's fantastic. I spent a lot of time over the years doing blue sky research. It's wonderful. but that's has nothing to do with the startup. It needs to have a clear idea of what is it going to sell.
Though I guess the tricky part with Earth observation and with sending satellites is that as soon as your satellite's in orbit, you have to. It's a bit like opening a supermarket in every country in the world, where you have to find uses for your data more or less everywhere at the same time. If you have, for example, an application which is very geographically constrained, you won't send a satellite. So you need to have it's maybe a chicken and the egg problem where the application will never arise if the data is not there. But then if the data is not there, then well, no one will actually take this data and create the application which will then serve the end client.
But the data, okay, so in some other industries, it may be, yeah, probably I would agree. But in this industry, the data is there, right? There are, I don't know, dozens of satellite imagery companies. There are hundreds of satellites flying at different orbits, collecting data at different resolutions, and hardly anybody is using it. I mean, I'm exaggerating, okay? There's huge defense industry where, countries spend hundreds of millions on buying this data, but it's nowhere near where people expected it to be, right? If you read some of these reports and aspirations by European Space Agency and NASA of of the economy that is going to emerge around the launch of the Sentinels and Landsat and all this, none of it materialized. Okay, so the data is there, but it's not being used. The question is why, and I think this is it's very important to try to figure out what is the bottleneck, why. And my answer to this is that there is no overlap between what is available, what is actually needed, and what is economically viable. Three sets separately, they're all nice and good, and they all full of activity, but they don't overlap. Okay. And so the challenge is, can you find something that would make them actually overlap? And that's the huge challenge.
And so your argument is that the economically viable part is the most sensitive part. And so let's say tomorrow all the prices of satellite data were to drop by 2 orders of magnitude. Would then many applications which are not feasible today become feasible? Or is it really the what is needed and what is technically possible, which don't overlap?
The price is one thing, but there's availability. The idea, the aspiration of satellite imagery is that you want to get an image of the point that you are interested in, okay, when you are interested in it, right? That's, for the most part, if it's different location, you don't care. If it's different time, you don't care. If it's 2 orders of magnitude more expensive than somebody is willing to pay you for the analytics, you don't care, right? So the question is whether you can create a system that would offer data where you need it, when you need it, at the price point that is reasonable, viable for the actual useful utility that this image can produce, right? It's actually quite simple. I mean, the equation is quite simple, but solving it proves to be incredibly difficult because there are lots of satellites, but there is enough that there is a small cloud that is passing by and you don't get an image and you need to reschedule for in 2 days. And then there is another cloud. Then in 3 weeks, you came back with an image, but nobody cares anymore. Yeah, so far it's open unsolved problem. And that's what Gamma Earth is trying to address in its own way, not in a perfect way, but in its own way. And I feel that we are on the right track.
So we're reaching towards the end of the episode. Is there anything you would like to add, or maybe resources that you would like to point to?
No, I think it's a very exciting industry. It's fascinating technology that I really enjoy working on, but it's also extremely complicated and hard, and in particular, trying to develop in commercial setting. Uh, so as long as you kind of do academic work, you just enjoy the, you know, tinkering with the technology, it's all nice, but then it becomes another magnitude more challenging if you are trying to actually build a viable business around it. And I wish everyone good luck in this space, because it is objectively very, very hard space to work.
Fascinating. Well, thank you very much. Thank you for the conversation. Thank you for your time.
Absolutely. My pleasure. Thank you, Louis.